June 14th, 1944. A captured American landing craft sat on a concrete pad at the Kriegsmarine testing facility in Wilhelmshaven, Germany. The vessel measured 36 feet in length, its plywood hull scarred from combat operations off the Normandy coast, where German forces had seized it intact just 8 days after D-Day. Kapitän See Heinrich Müller, chief naval architect for the Reich's Amphibious warfare development program, circled the craft with growing disbelief. His team had spent the morning disassembling the boat's major components, photographing each system, measuring every joint and fastener. What they discovered contradicted everything the Kriegsmarine had assumed about American industrial capability and marine engineering principles. The boat before them, officially designated Landing Craft Vehicle, Personnel, or LCVP in American terminology, represented something far more threatening than its simple appearance suggested. This was not advanced technology. The construction was almost primitive by German engineering standards. Plywood sides, a basic automobile engine, rudimentary controls, welded steel components that showed minimal finishing work. Yet this crude vessel had carried 36 soldiers through rough channel waters, deposited them on a defended beach, and survived long enough to make the return journey. More disturbing still were the production markings stamped into the vessel's identification plate. Built by Higgins Industries, Incorporated, New Orleans, Louisiana, hull number 7412. Completion date April 19, 1944. 7412. Müller had reviewed intelligence estimates suggesting American landing craft production numbered in the thousands, but seeing physical evidence was different. This particular boat had been built less than 2 months before its capture, one of thousands flowing from American shipyards at rates that seemed impossible. The German amphibious craft program, despite years of development and the full resources of the Reich's industrial system, had produced fewer than 800 specialized landing vessels of all types since 1939. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The question that brought Müller and his team to Wilhelmshaven on that June morning was both technical and strategic. How had American builders created a vessel that could be manufactured in such quantities while maintaining adequate performance? The answer they found would reveal not just a successful boat design, but a complete reimagining of how complex military equipment could be produced when engineering sophistication gave way to manufacturing pragmatism. The revelation would come too late to alter Germany's fate, but it would fundamentally challenge assumptions that German naval architects had carried throughout the war about the relationship between quality, complexity, and industrial capacity. The journey to that moment of recognition began not in Germany's defeat, but in America's desperation. In the summer of 1940, as German forces completed their conquest of France and prepared for a potential invasion of Britain, the United States military faced a capability gap that threatened to undermine any future amphibious operations. The U.S. Marine Corps and Army possessed virtually no specialized landing craft suitable for opposed beach assaults. The few vessels available were converted civilian boats or experimental designs that had never been tested in combat conditions. Traditional military procurement processes called for extensive research, prototype development, competitive bidding, and careful evaluation before production contracts were awarded. That methodology typically consumed 3 to 5 years from initial requirement to delivered. Equipment. The War Department understood by late 1940 that America might need to conduct massive amphibious invasions within 2 years. The mathematics were unforgiving. To land a single infantry division, approximately 15,000 men with vehicles, artillery, and supplies, planners estimated they would need at least 1,500 individual landing craft trips. A corps-sized invasion of 3 divisions would require 4,500 craft movements. The contemplated invasion of Europe, whenever it might occur, would demand landing craft numbered in the tens of thousands. No existing American manufacturer had experience building such vessels at scale. The Navy's Bureau of Ships, responsible for military vessel acquisition, began searching for someone who could solve an impossible problem. produce thousands of specialized boats, make them simple enough for rapid manufacture, robust enough for combat operations, and deliver them fast enough to meet invasion timelines, that kept advancing as the war situation deteriorated. The search led them to a boat builder in New Orleans, who had never designed a military craft, never worked on a government contract, and ran a company that mostly built pleasure yachts and commercial workboats for the Gulf Coast fishing industry. Andrew Jackson Higgins was 54 years old in 1940 when the Navy first contacted him, a self-made entrepreneur whose formal education had ended at grammar school. He'd spent his career building boats by intuition and trial and error, creating designs that worked rather than designs that pleased naval architects. His boats had reputations for reliability in the harsh Gulf environment, but nobody, including Higgins himself, considered them sophisticated engineering. What Higgins possessed instead of formal credentials was an intuitive understanding of practical boat-building fundamentals. He knew that simple designs were more reliable than complex ones. He understood that standardized components allowed rapid production. He recognized that construction methods mattered as much as design excellence. Most importantly, he had no reverence for traditional approaches that claimed certain features were essential or certain construction sequences were mandatory. If something worked, it was correct, regardless of what established practice dictated. The Bureau of Ships' initial requirements called for a landing boat that could carry a platoon of troops, approximately 36 men, approach a beach at high speed, discharge the soldiers quickly, and retract from the surf before enemy fire destroyed the vessel. The boat needed a draft shallow enough to reach the beach but sufficient power to handle open ocean waves. It required armor protection for the crew and passengers, but couldn't be so heavy that existing ship davits couldn't lift it. The specifications ran to 47 pages of detailed requirements covering everything from turning radius to fuel capacity to maintenance accessibility. Higgins read the requirements once, set them aside, and began sketching. His design approach started not with the specifications, but with the fundamental problem. Getting men from ship to shore through surf and enemy fire with maximum simplicity and minimum cost, every feature would be justified by that mission. Anything that didn't directly contribute would be eliminated. The Bureau wanted armor plate protection. Higgins countered that armor heavy enough to stop bullets, made the boat too heavy to beach properly and too expensive to build in quantity. Better to make thousands of unarmored boats that could swarm a beach than hundreds of armored boats that got stuck in the surf. The Bureau insisted on diesel engines for safety and fuel efficiency. Higgins argued that automotive gasoline engines were available in quantity from existing suppliers, mechanics already knew how to maintain them, and parts were standardized across hundreds of thousands of vehicles. Diesel would create supply chain complications and maintenance challenges that mattered more than theoretical efficiency advantages. The Bureau required sophisticated communications equipment. Higgins eliminated it. Landing craft would operate in visual contact with control vessels. Complex radios would fail in the harsh marine environment and required trained operators the military didn't have in sufficient numbers. The confrontation between Higgins' pragmatic simplicity and the Bureau's engineering sophistication came to a head in December 1940 during official trials of competing landing craft designs. 4 manufacturers had submitted prototype boats. 3 were designed by naval architects with impressive credentials, built in established shipyards, and incorporated advanced features that the Bureau's evaluators found technically impressive. Higgins' boat was plywood and steel, powered by a car engine, controlled by a steering wheel taken from a truck, and looked like something a backyard builder might construct on a weekend. The trials were conducted in the Chesapeake Bay during winter conditions. Waves ran 4 to 5 feet, water temperature was 41 degrees, wind gusted to 25 knots. Conditions that simulated actual combat operations. The sophisticated designs performed admirably in calm water but struggled in rough conditions. Complex systems failed. Carefully engineered features proved fragile. One boat swamped when waves exceeded its freeboard. Another's custom-designed engine couldn't maintain power in high sea states. The third made it to the beach but couldn't retract through the surf. its precisely calculated hull shape digging into the sand. Higgins' boat was crude, loud, and sprayed water over everyone aboard. It also worked. The flat bottom and simple spoon-shaped bow rode over waves that swamped deeper hulls. The automotive engine, while unsophisticated, delivered consistent power because it was designed for variable loads and harsh conditions. When the boat reached the beach, its shallow draft and flat bottom let it drive right up onto the sand. When the coxswain threw the engine into reverse, the boat simply backed off the beach and headed back out through the surf. The observers, many of whom had initially dismissed Higgins' design as amateurish, watched the boat make repeated runs while the sophisticated design sat broken or stuck. The demonstration proved a principle that would define American military production throughout the war. Adequate equipment available in quantity defeated excellent equipment available in limited numbers. In February 1941, the Navy awarded Higgins Industries a contract for 1,000 landing boats. The Bureau of Ships still harbored doubts, but combat urgency overrode engineering preferences. Higgins promised delivery would begin within 6 months. Navy procurement officials, accustomed to multi-year delivery timelines, considered this optimistic fantasy. The challenge Higgins faced was not designing the boat but creating a production system that could build them at unprecedented rates. Traditional boat building was a craft process. Skilled workers shaped individual pieces, fitted them together, adjusted components until everything aligned properly. Each boat was essentially custom-built, even when following standard plans. Construction time for a 36-foot vessel using conventional methods averaged 6 to 8 weeks per unit. Higgins needed to produce boats in days, not weeks. His solution drew inspiration from automobile assembly lines, but adapted those principles to wooden boat construction in ways that would horrify traditional boat builders. The first radical departure was complete standardization of components. Every piece of wood in a Higgins boat was pre-cut to exact dimensions before construction began. Frames, sides, bottom panels, bulkheads, seats, every component was fabricated from master, the patterns, then stacked in organized inventories near the assembly stations. Workers building boats never measured or cut. They selected pre-made pieces and fastened them together. The plywood sides came from suppliers as large panels marked with assembly reference points. Workers didn't determine where fasteners should go. They lined up marks and drove screws at designated locations. The steel ramp, the boat's most distinctive feature, arrived as a prefabricated assembly that bolted to the bow with 8 standardized fasteners. The automotive engines came from manufacturers completely assembled and tested. Installation required connecting 4 mounts, 1 throttle cable, 1 fuel line, and 1 exhaust pipe. The entire engine installation process took 2 workers approximately 45 minutes. The second transformation was spatial organization of the construction process. Higgins divided his factory floor into 16 sequential stations. Each station performed one specific set of tasks. Station 1 assembled the basic frame structure. Station 2 installed the bottom panels. Station 3 added the side panels. Station 4 installed bulkheads and structural reinforcements. Every boat moved through these stations on rolling jigs that required no special handling equipment. Workers pushed completed boats to the next station, where different teams took over. This sequential flow meant that 16 boats were under construction simultaneously at different completion stages. When Station 16 finished a boat, all 16 stations pushed their boats forward. One completed vessel rolled off the line, and a new frame assembly started at Station 1. The cycle repeated every 4 hours initially, 3 times per working day. As workers gained experience and processes were refined, cycle time dropped to 3 hours, then 2.5 hours. By mid-1941, Higgins Industries was completing 8 landing boats per day. The skeptics in the Bureau of Ships, who had predicted production disasters, were forced to acknowledge that Higgins' crude methods were producing boats at rates no traditional shipyard could match. The workforce assembling these boats reflected Higgins' unconventional approach as thoroughly as the construction methods. Traditional boatyards recruited from maritime communities where skills passed through generations. Higgins advertised in New Orleans newspapers for workers with no experience required. Training provided. He hired women, African Americans, and anyone else willing to learn, a radical departure from the segregated employment practices common in 1941 Louisiana. The training program was as pragmatic as the boat design. New workers didn't learn comprehensive boat building. They learned one specific task at one specific station: how to align and fasten side panels, how to install engine mounts, how to attach ramp hydraulics. Training took 1 to 2 weeks, after which workers became productive contributors to the assembly line. Josephine Davis, hired in April 1941 with no prior manufacturing experience, described the training process in a 1943 interview preserved in the National World War II Museum archives. They showed me how to drill pilot holes for screws in the plywood sides, how to align the panels using the reference marks, and how to drive screws with the pneumatic drivers. That was my job. I did it 40 times a day, every day, for 2 years. I got very good at it. My station's reject rate was under 1%. The simplification of complex work into repetitive, simple tasks proved devastatingly effective. By August 1941, Higgins employed over 3,000 workers, most with less than 6 months' experience, building boats faster than experienced craftsmen in traditional yards had thought possible. The quality control system reinforced the standardization approach. Rather than relying on skilled workers to build boats correctly, Higgins assumed workers would make mistakes and designed verification steps to catch errors before they propagated. Each station had inspectors who checked specific features: side panel alignment, fastener spacing, ramp operation, engine installation. Boats didn't move to the next station until inspectors approved the current stage. Defects found at Station 10 were traced back to the station where the error occurred. That station's procedures were examined and modified to prevent recurrence. This systematic quality approach was unusual in 1941 manufacturing. The prevailing philosophy assumed that skilled craftsmen produced quality work through expertise. Higgins' system assumed errors were inevitable and created processes to detect and correct them systematically. The approach anticipated modern quality management methodologies by decades. The dramatic escalation in production requirements came after Pearl Harbor, on December 7, 1941, when Japanese forces attacked the Pacific Fleet. America's military situation transformed overnight from theoretical preparation to desperate emergency. The Navy immediately began planning offensive operations across the Pacific that would require amphibious assaults on defended islands. The scale of landing craft requirements exploded from thousands to tens of thousands. In January 1942, the Navy increased Higgins' contract from 1,000 boats to 5,000 boats with options for unlimited additional orders. The delivery timeline collapsed from comfortable monthly schedules to desperate pleas for maximum possible production. Higgins faced a challenge that would have paralyzed traditional manufacturers: how to increase production tenfold without proportionally increasing facility size, workforce, or construction time per unit. The solution required another conceptual revolution. Higgins had already maximized efficiency within his existing factory. Further production increases required building additional factories, but conventional wisdom said new facilities needed years to become fully productive. Experienced workforces couldn't be created overnight. Complex construction processes couldn't simply be replicated in new locations. Higgins rejected that conventional wisdom. If processes were sufficiently standardized and documented, new factories could be productive within weeks. If training programs were adequately developed, new workers could contribute immediately. If components were properly prefabricated, construction complexity disappeared. Between January and July 1942, Higgins Industries opened 7 additional manufacturing facilities across New Orleans. Each new factory was essentially a copy of the original, with identical station layouts, identical component inventories, identical quality control procedures. Workers trained in the original facility transferred to new locations to establish procedures and train new hires. Within 3 weeks of opening, new factories were producing boats at rates comparable to the original facility. The expansion revealed another advantage of Higgins's standardized approach. Because components were fabricated separately from final assembly, Higgins could subcontract component production to hundreds of smaller suppliers. Plywood panels were cut by furniture factories, steel ramps were fabricated by structural steel shops, engines came from automotive plants, propellers were cast by industrial foundries. Higgins factories became assembly operations that integrated components from a vast supply network. By mid-1942, over 200 companies across 15 states were producing components for Higgins boats. This distributed production system provided resilience against disruption. When one supplier faced labor shortages or material constraints, others compensated. No single bottleneck could halt production. The approach also multiplied production capacity without requiring Higgins to build massive factories or employ enormous workforces directly. The final evolution of the design came in response to a critical operational requirement identified during the Guadalcanal campaign in August 1942. The Marine Corps reported that while Higgins boats successfully delivered troops to beaches, they couldn't land vehicles. Tanks, trucks, artillery and supplies had to be transferred to shore using improvised methods that were slow, dangerous, and often impossible under enemy fire. The Navy requested that Higgins modify his design to allow vehicle transport. The requirement seemed to demand a completely new boat. Vehicles needed a front-loading ramp rather than troop disembarkation over the sides. The boat needed to be longer and wider to accommodate jeeps and light tanks. The structure needed reinforcement to handle vehicle weight. Traditional design approaches would have required months of engineering studies, prototype development, and testing. Higgins made sketches for 2 weeks, built a prototype in 30 days, and had it tested by Marine Corps evaluators in September 1942. The vehicle version, designated Landing Craft Mechanized, or LCM, retained the fundamental architecture of the troop carrier: plywood construction, automotive engine, simple controls, standardized components. The modifications were pragmatic rather than sophisticated. Make it longer, widen the beam, add a ramp at the bow, reinforce the bottom with additional frames. The Marines tested the prototype by driving a 4-ton truck aboard, running it out to a beach and unloading. The operation took 7 minutes. The evaluators approved the design immediately. By December 1942, Higgins factories were producing both troop carriers and vehicle carriers, using the same basic production methods, the same workforce, and the same supply networks. The vehicle version required slightly longer construction time, approximately 5 hours per unit initially, but process refinements reduced that to 3 hours by early 1943. The statistical impact of Higgins' production system becomes clear in the aggregate numbers. Between 1941 and 1945, Higgins Industries and its licensees produced approximately 20,300 landing craft of various types. This represented roughly 60% of all American landing craft built during the war. At peak production in 1944, Higgins facilities were completing over 700 boats per month, approximately 23 boats per day across all factories. The construction time per boat had fallen from the initial 12-hour cycle to an average of under 4 hours by mid-1943. The fastest documented completion time, achieved during a demonstration for Navy inspectors in March 1944, saw a complete boat built from first component assembly to water trials in just 7 hours and 12 minutes. The workforce employed by Higgins Industries peaked at approximately 25,000 workers in 1944. Of these, approximately 45% were women, a remarkable proportion for heavy manufacturing in that era. African American workers comprised roughly 30% of the workforce, employed in all roles including supervisory positions, an unusual level of integration for 1940s Louisiana. The economic efficiency proved as revolutionary as the production speed. The first Higgins boats cost approximately $4,800 each to manufacture. By 1943, costs had fallen to $3,200, despite rising material prices and labor wages. The cost reduction reflected learning curve effects and process improvements that came from building thousands of identical units. Each landing craft, vehicle, personnel cost roughly what the military paid for 6 jeeps. For that investment, commanders received a boat that could deliver 36 soldiers or a jeep and 12 soldiers directly onto a defended beach. The return on investment, measured in military capability per dollar, exceeded virtually every other equipment program. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German evaluation of the captured Higgins boat that brought Kapitän Müller to Wilhelmshaven in June 1944 occurred against this production and operational background, though the German analysts didn't yet know the full scale of what they were examining. The intelligence estimates they possessed suggested American landing craft production numbered in the low thousands. The reality of over 20,000 boats would not become clear until after the war, when captured documents revealed the true numbers. What Müller and his team could determine from physical post-inspection was disturbing enough. The disassembly process began with the ramp mechanism, the most distinctive feature of the boat, and the component German engineers found most puzzling. The hydraulic system that raised and lowered the ramp consisted of a simple automotive hydraulic cylinder, the type used in truck dump beds, connected to the ramp through basic mechanical linkages. The entire assembly contained perhaps 24 parts. German amphibious craft used electrically powered winch systems with complex gear trains and elaborate control systems. The American approach was crude but functional. The hydraulic cylinder could lift the ramp in approximately 4 seconds, compared to 12 seconds for German electric winches. The simplicity meant field maintenance required only basic tools and common hydraulic fluid. The hull construction proved even more troubling to German assumptions about proper marine engineering. The bottom and sides were 3/4-inch marine plywood, A, material German naval architects had never specified for military craft. Plywood was considered suitable for interior joinery or temporary structures, not for hulls that would experience combat loads and harsh marine environments. Yet the captured boat's hull showed minimal deterioration, despite obvious combat use. The plywood had been treated with preservative and sealed with marine paint, but the material itself was simply standard industrial plywood. Müller's technical report, declassified in the 1980s, captured the cognitive dissonance this created. We specify steel or aluminum for landing craft hulls, as these materials provide necessary strength and durability. The Americans use plywood, a material we rejected as inadequate, yet their boats demonstrably function in combat conditions. This suggests either their combat requirements are less demanding than ours, which operational intelligence contradicts, or our material assumptions are incorrect. The engine installation revealed another philosophical divide. German military boat engines were purpose-designed marine power plants, with specialized components, custom instrumentation, and elaborate starting systems. The Higgins boat used a grey marine 6-cylinder gasoline engine that was fundamentally a Chevrolet truck engine modified for marine use. The modifications were minimal: a different carburetor, marine-grade ignition components, and a raw water cooling system. The engine developed 125 horsepower, adequate but not impressive. What impressed the German evaluators was the parts commonality. Every major component, pistons, crankshaft, connecting rods, cylinder head, was interchangeable with standard Chevrolet truck parts. Field maintenance could be performed with automotive tools. Replacement engines were available from the massive American automotive production infrastructure. Oberingenieur Klaus Werner, the Kriegsmarine's lead propulsion engineer assigned to the evaluation team, noted in his analysis, their marine engine is inferior in specific power and fuel efficiency compared to our purpose-designed units. However, their approach provides unlimited spare parts, simplified training, and rapid replacement capability. In extended operations, logistics sustainability may matter more than technical excellence. The control systems embodied the same pragmatic philosophy. The boat was steered using a standard automotive steering wheel connected to the rudder through simple mechanical linkages. Engine throttle was controlled by a hand lever, similar to those used in trucks. There were no sophisticated instruments, no elaborate control panels. A compass, an engine tachometer, and a fuel gauge comprised the entire instrument array. German landing craft had dedicated coxswain stations with multiple instruments, communication equipment, and specialized controls. The American station consisted of a truck steering wheel and 2 levers. The structural engineering revealed the most profound difference in design philosophy. German landing craft were engineered to specific stress calculations with safety margins determined by rigorous analysis. Structural members were sized precisely for calculated loads. The American boat appeared to use a simpler approach: make every structural component stronger than necessary. The frames were heavier than stress analysis would require. The fasteners were more numerous than calculations suggested necessary. The plywood was thicker than minimal requirements demanded. This approach, which German engineers initially interpreted as crude over-engineering, actually reflected sophisticated understanding of manufacturing realities. Precise optimization required precise construction, which was difficult to achieve in mass production. Generous over-design allowed looser tolerances without compromising safety. Workers didn't need to understand complex stress analysis. They just needed to follow procedures that inherently provided adequate strength. The assembly methodology fascinated the German team perhaps more than any individual component. The captured boat showed evidence of rapid construction. Fastener spacing was regular but not perfectly uniform. Some welds showed spatter that would have been cleaned up in German practice. Paint application was functional but not cosmetically refined. Yet nothing was actually defective. The boat was serviceable, just not beautiful. Werner's technical assessment concluded, "The Americans have created a manufacturing weapon rather than an engineering achievement. The boat is unsophisticated, but that unsophistication enables production at scales we cannot match. Our landing craft are superior vessels individually. Their landing craft are adequate vessels available in numbers that render quality comparisons irrelevant." The strategic implications emerged as German intelligence compiled reports from multiple captured boats and prisoner interrogations. By July 1944, the Kriegsmarine understood that American landing craft production measured in the tens of thousands, not thousands. The realization triggered a reverse engineering program that aimed to adopt American production methods for German amphibious craft. The program was stillborn. Germany's industrial system in mid-1944 lacked the resources, infrastructure, and most critically, the time to implement such a transformation. The philosophical confrontation between German engineering sophistication and American manufacturing pragmatism extended beyond landing craft to become a defining pattern of the war. German equipment was generally more technically advanced, more precisely engineered, more carefully finished. American equipment was adequate, standardized, and available in crushing quantities. The Tiger tank was superior to the Sherman tank in armor, firepower, and battlefield performance. But America built 50,000 Shermans. Germany built fewer than 1,500 Tigers. The Me-262 jet fighter was faster and more advanced than any American fighter, but it arrived too late and in too few numbers to affect air superiority that American P-51 Mustangs had already established through numerical dominance. The pattern repeated across every category of equipment. German submarines were sophisticated but scarce. American destroyers and destroyer escorts were basic but numbered in the hundreds. German artillery was precision-engineered. American artillery was mass-produced. Quality confronted quantity, and quantity won through brutal mathematics. Landing craft embodied this confrontation perhaps more clearly than any other equipment category. The mission was simple: move men and material from ship to shore. Technical sophistication didn't make boats accomplish that mission better. Availability meant commanders could execute operations that sophisticated but scarce craft made impossible. The invasion of Normandy on June 6, 1944, provided the ultimate demonstration of what Higgins's manufacturing revolution enabled. Operation Overlord employed approximately 5,300 landing craft of various types, delivering 156,000 soldiers across 50 miles of fortified coastline in a single day. The assault phase required approximately 23,000 individual craft movements over 48 hours. No military operation in history had ever attempted amphibious assault at that scale. The operation was conceivable only because American yards had produced landing craft at rates that made the seemingly impossible merely difficult. Of the landing craft employed at Normandy, approximately 65% were Higgins-built boats or license-built copies of Higgins designs. The LCVPs delivering infantry, the LCMs carrying vehicles and artillery. These were the boats that thousands of soldiers remembered for the rest of their lives. Crowded, uncomfortable, soaked with spray, deafening from engine noise, and absolutely crucial to getting ashore alive. The after-action reports from Normandy documented landing craft performance with brutal clarity. Approximately 2,600 landing craft were lost to enemy action, accidents, or weather during the Normandy operation. This represented roughly half the craft committed to the assault, yet the invasion succeeded because replacement boats arrived continuously. Ships offshore carried spare landing craft on davits. Repair crews patched damaged boats on the beaches. Most critically, the vast production capacity meant lost boats didn't constrain operations. Commanders could accept 50% losses because the remaining boats still sufficed to land the force. A German amphibious operation planned around scarce, sophisticated craft couldn't absorb such losses. German planners were forced to treat landing craft as irreplaceable assets, which constrained operational planning and forced conservative approaches. American planners treated landing craft as expendable commodities, which enabled aggressive operations that accepted high loss rates to achieve rapid strategic results. The psychological impact on commanders who understood the implications was profound. General Omar Bradley, 1st Army commander during Normandy, reflected on landing craft availability in his post-war memoir. We planned Overlord assuming approximately 40% landing craft losses in the assault phase. Such losses would have been catastrophic if craft were irreplaceable, but we knew American yards were building boats faster than we could lose them. That knowledge enabled operational audacity that would have been reckless with limited resources. The Pacific War demonstrated the same principle across an even larger theatre. Between 1943 and 1945, American forces conducted 51 major amphibious assaults across thousands of miles of ocean. Each operation required hundreds or thousands of landing craft. The boats were destroyed by enemy action, wrecked on coral reefs, lost in typhoons, or simply worn out by hard use in harsh conditions. None of it mattered strategically, because production exceeded losses by factors that made attrition irrelevant. The assault on Okinawa in April 1945 employed over 1,400 landing craft, delivering 183,000 troops in the initial assault wave. Japanese forces destroyed approximately 400 craft through kamikaze attacks, coastal artillery, and mines. The operation continued without pause because replacement boats were available. The island was secured despite landing craft losses that would have halted any previous amphibious campaign in history. Admiral Richmond Kelly Turner, who commanded amphibious operations in the Pacific, testified before Congress in 1946 about the strategic impact of landing craft production. Island hopping across the Pacific was possible only because we had landing craft in unlimited supply. Each assault consumed boats like ammunition. We lost hundreds on reefs, to enemy fire, to storms. If craft were precious and scarce, we would have been forced to slow our advance, giving Japan time to fortify positions and extend the war. Unlimited landing craft meant unlimited operational tempo. We moved faster than the enemy could prepare defences. That pace, enabled by industrial capacity, shortened the war and saved lives. The cost-benefit analysis of Higgins' production approach becomes starkly clear in comparative statistics. Germany produced approximately 780 specialized landing craft of all types between 1939 and 1945. These boats were well-engineered, carefully built, and individually capable. They also cost approximately 32,000 Reichsmarks each, equivalent to roughly $12,800 at wartime exchange rates. German landing craft cost 4 times more than Higgins' boats and were produced at 1/26 the rate. The production differential translated directly into operational capability. Germany could land approximately 1 division simultaneously with its available landing craft inventory. The United States could land 7 divisions simultaneously using just the craft assigned to the European theater. In the Pacific, American forces could execute multiple major amphibious assaults concurrently, something Germany's landing craft inventory made impossible even if strategic circumstances had required it. The human cost avoided through landing craft availability is harder to quantify but historically significant. Amphibious assaults with inadequate craft forced soldiers to wait in follow-up waves, extending their exposure to enemy fire. Insufficient boats meant congested beaches where troops and vehicles concentrated in vulnerable killing zones. Higgins's production rates ensured that planners could employ enough craft to land forces rapidly, reducing time in the vulnerable approach phase and minimizing beach congestion. Casualty studies suggest that landing craft availability directly correlated with assault casualties. Operations with high craft-to-troop ratios like Normandy, where 5,300 craft landed 156,000 soldiers, a ratio of approximately 1 boat per 30 soldiers, experienced lower casualty percentages than predicted. Operations with lower craft ratios showed higher casualties. The correlation wasn't perfect. Many factors affected casualties, but the pattern was clear enough that operational planners specifically requested maximum landing craft allocation for assaults where heavy resistance was anticipated. The post-war career of Higgins Industries illustrated the challenge of transitioning from wartime emergency production to peacetime manufacturing. Between 1945 and 1946, landing craft orders collapsed from hundreds per month to 0. The massive workforce that had built boats with assembly line efficiency was no longer needed. By March 1946, Higgins Industries employed fewer than 800 workers, down from the wartime peak of 25,000. Andrew Higgins attempted to convert his factories to civilian boat production, building pleasure craft and commercial vessels, using the same efficient methods that had made military boats. The attempt failed. Civilian customers demanded customization, elaborate finishing, and features that mass production methods couldn't economically provide. The very standardization that enabled wartime production became a liability in peacetime markets, where customers wanted boats tailored to individual preferences. Higgins Industries declared bankruptcy in 1948. The factories that had produced 20,000 landing craft closed permanently. Andrew Higgins, who had revolutionized amphibious warfare and enabled Allied victory through manufacturing innovation, died in 1952 with limited recognition for his contributions. He never received a major award or governmental decoration. His name was largely forgotten outside naval historical circles, yet the impact of his work extended far beyond the boats themselves. The production methodologies Higgins pioneered, standardized components, assembly line manufacturing, distributed supply networks, simplified training, influenced post-war American manufacturing across industries. The techniques developed in New Orleans shipyards informed post-war automobile production, appliance manufacturing, and consumer electronics industries. The philosophical approach of adequate equipment in quantity rather than perfect equipment in scarcity became a fundamental principle of American industrial strategy. Modern amphibious warfare remains dependent on landing craft, whose fundamental design derives directly from Higgins' innovations. The landing craft air cushion, currently used by the U.S. Navy for amphibious assaults, employs hovercraft technology that didn't exist in the 1940s, but the operational concept remains identical. Transport troops and vehicles from ship to shore through hostile environments using craft that are simple, reliable, and available in sufficient numbers. The design philosophy that Higgins established, optimize for manufacturing and operational simplicity rather than technical sophistication, persists in modern amphibious craft development. The captured boat that Kapitän Müller examined in June 1944 remains in a German naval museum, one of only 3 surviving Higgins boats in Europe. The vessel's identification plate, hull number 7412, sits in a display case alongside Müller's technical evaluation report. The report's conclusion, declassified and published in the 1990s, provided a fitting epitaph for German engineering sophistication confronting American industrial pragmatism. The American landing craft represents a philosophical approach to military equipment that the Reich failed to understand until too late. They did not build the best boat. They built an adequate boat that could be produced in unlimited numbers with available resources and unskilled labor. Our boats were superior individually. Their boats were sufficient collectively. In war, sufficient equipment available everywhere defeats superior equipment available nowhere. This lesson, written in Plywood and automotive engines, may be the Americans' most important technical achievement. Not their radar, not their atomic weapons, but their recognition that war is fundamentally a production contest, and victory goes to the side that can sustain material superiority long enough for quality differences to become irrelevant. The story of how German engineers tested a captured Higgins boat and admitted it could be built in days. What took them months is ultimately a story about the relationship between sophistication and effectiveness. Andrew Higgins built crude boats with automotive engines and plywood hulls. German engineers built precision craft with purpose-designed components and sophisticated control systems. On paper, German boats were superior. In practice, American boats won the war. The difference wasn't technical excellence, it was manufacturing philosophy. Higgins understood that wars are won with equipment that exists, not equipment that could theoretically be designed. He recognized that adequate craft available in June meant more than perfect craft promised for December. Most crucially, he knew that military equipment serves strategy, and strategy that depends on scarce resources fails when those resources aren't available in the quantities operations demand. The 20,000 landing craft Higgins Industries produced between 1941 and 1945 carried more than soldiers and vehicles across hostile beaches. They carried proof that manufacturing capacity is a strategic weapon as decisive as any advanced technology. They demonstrated that pragmatic simplicity often defeats sophisticated complexity when scale and availability matter more than individual performance. They validated the principle that wars are fundamentally contests of production, and the side that can manufacture adequate equipment faster than the enemy can destroy it holds advantages that tactics and technical superiority cannot overcome. The plywood boats that horrified German naval architects and impressed American generals were never beautiful. They were never sophisticated. They were never engineering triumphs that inspired technical admiration. They were simply available in crushing numbers when and where military operations demanded them. In the calculus of war, that availability mattered more than any technical feature could have mattered. Higgins' legacy lives not in museums or monuments, but in the continuing recognition among military planners and industrial strategists that production capacity is a weapon system, that logistical availability determines operational possibility, and that the equipment in hand, however crude, defeats the perfect equipment still on the drawing board every single time. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.